I said people don't listen to me. I need to organize it to. Particularly.
I'll do Portuguese. How's that?
Okay, we'll start the second talk. Second talk is by Nathan Kutz. I think my pronunciation is okay, right? And he's going to talk about the waterway problem again. Thank you.
All right. First of all, let me say I'm really not a fluids person, as most of you know. However, I got sucked into this problem by John because I was so attracted by his movies. Essentially, he came up and visited Washington, and we started talking, and then I'll show you sort of the evolution of how this happened. But one of the things I do enjoy quite a bit is I've very greatly enjoyed being in this crowd. This is a fantastic crowd of people. So I might have to stay in fluids just to hang out with you guys more often. And with that said, let me just be the first to announce Waves and Fluids 4 in July. It happens to be in July 2014. Is that right, Andre? Yeah. And at least we have some initial commitments here. 2 people already accepted. I'm coming in, and you know John will be here. So we got to work on this to make this happen somehow. It could be even maybe just John and I show up for Fluids 4.5 or 3.5, whatever happens to be, July 2014. It might just happen to be the week before the World Cup final. So. Okay. Yeah, exactly. You're going to get everybody wanting to sign up for this. All right, with that, let's start off with what I want to talk about. So I got interested in John's work partly because I started teaching a class on data analysis. So I wanted to learn some stuff, so the best way to learn new material is teach a class. So I started teaching this course, but I wanted a different angle on it, which is, in some sense, there is a lot of data analysis courses on our campus. You find them in the statistics departments. You find them partly in computer science, where they're doing machine learning. And part of the way they think about these things, especially the statisticians, is you have data. It's kind of this static thing. And really what I wanted to do with it is think about the data as telling you something about a system and thinking about building dynamics from that, directly from your data. And so this is how they think about it, but you can find a lot of examples of nice data analysis and image processing, computational finance, etc. They often do your principal component analysis, which you find the most important features of the data, project things down onto those features in some way, and then often use statistics to do some things with that data, including machine learning and so forth. So this is a fast-growing area. Computer science in our university is hiring in this direction, and people very interested in taking this big sets of data. And in Seattle in general, we have Microsoft, Google, Amazon. And what they want to do is grab data, do machine learning on it, to sell you more stuff. Okay, and it's a pretty serious effort. They'll pay basically right now kids coming out with a BS degree, $110K a year, $20,000 signing bonus, and that's their whole job, is to come in, take the data, process it, do machine learning. Where should I place an ad? What ad should I place? They charge by location. They've done all this statistical stuff on it. So part of it, there's a machinery here that kind of works, and there's no physics in that. But part of what I wanted to say is let's take some of these techniques now and put physics into it. So I'm going to start off with a picture that I think tells you 1,000 words, right? Which is, although principal component analysis might be quantitatively new to us, I would argue, in fact, it's an old idea. And Picasso, I think, hit it right on the head with this picture, this simple little drawing. How much do you think that's worth? A lot of money. I could draw that dog. I could sketch one right here on the board for you. Ready? Now, don't erase the board ever, because this can be worth something. You just do something like this, and, a little... It's not bad? It's okay? Yeah. The signature is very important, yeah. But he was on to something. In fact, artists were playing a lot with this idea early during this period, which is, how much information can I convey to you in a simple representation? What is the minimal representation of a dog? Not only do you know this is a dog, you know exactly what type of dog. This is remarkable from this little sketch. But what I would say is this represents all the key ideas of principal components, dropping it down onto some optimal, low-rank system. And what we want to do is do the same thing for PDEs, the water wave problem or some others I'll talk about, which is to say you have some dynamics. It can look very complex. But if I want to get the key behavior, it's not clear I need to get all the detail. What I need to get is the key features of that dynamic, and who cares about the details? I don't see any fur, eyes, mouth, tongue. If I'm trying to convey to you a dog, that's all I need. Okay? So let's try to do this same thing within the context of PDEs. Everybody's good with that? All right. So there's the dog. All right. So we all do PDEs. And here's the simple way to solve PDEs. You start off. The first thing you try to do is turn it into ODE. That's why an ODE course is usually required before your PDE course, because you work really hard at turning it into ODE. Once you get it in ODE form, you just try to turn it into algebra. And then you undo the process. So we train our students to think, oh yeah, this is not bad. We give them all these nice linear constant coefficient problems, and they get the mistaken idea that they can solve a lot of stuff. And they can't, right? Because any modern research, you're going, well, this step here, these 1, 2, 3s are very hard to do. And in certain cases you can do it, but probably not. Take a look at John's problem. Tell me if you can find 1, 2, 3 for that problem. This is a difficult problem, and so what you do is you turn to the computer often. Right? So what we want to generically do, solve some nonlinear PDE. What's that? No, John. Just John. Just John. That John. Okay, John W. And John B. Okay. So here's one way to reduce this. You take this thing, you expand in a basis set. Right? This is the standard technique. This is the first thing we do. This is the oldest trick in the PDE book. When you start teaching PDEs, you say, hey, let's talk about this in terms of separation of variables, and we get an ODE, an ODE, we solve. Now, when you do this in a nonlinear problem, first, it doesn't work in an analytic sense, but what we can say is, well, if I do this and I expand in Fourier basis, for instance, and I would want to expand in a Fourier basis simply because I get n log n speed, spectral accuracy. If I take enough modes, even though I have a nonlinearity here which would mix all these modes, if I capture enough modes, fine. I'll just feed energy back and forth between the nonlinear modes, no problem. But it still begs the question, how should you pick this basis to begin with? Right? We might pick Fourier modes, for instance, and Fourier transforms simply because we really know, we have a very good intuitive feel for what Fourier modes are. They're n log n speed, they're spectrally accurate, and so you just program this up. There you go. And so you solve your problem with some method like this, for instance. But shouldn't you pick that in a better way, perhaps? How many modes was John using in his water waves? 10,000. 10,000. You see this water wave, you got 10,000 modes. Maybe there's another way to do this, and maybe what we want to do is we want to just basically figure out what, in fact, is the optimal basis to pick and then project our dynamics there. So I'm not going to go through this except for there's the system that John set up. Okay, you have this surface you're trying to solve for. You're trying to solve for the motion of the fluid inside, solve for the surface and how it's behaving in time. We're going to look at time periodic standing waves, essentially. And using this boundary integral method, there it is. John, of course, went into detail there, so I'm not going to say much about it except for that you can recast some things here, all in terms of this dipole density mu. That'll become important in a minute. And then here's these movies again. Now, let me just show you the movie and then show you what the motivation then was for the work that came out of this. So here is sort of a low amplitude solution to this thing. And on some level, you say, oh, look at that. That kind of looks like sinusoidal behavior. I could probably do expanded Fourier modes pretty simply with this. It's a very simple behavior. Okay? But here is the more interesting one. John showed you a whole zoo of these things. These are kind of more, let's call them exotic, right? So if you try to use Fourier modes, you'd say, well, I mean, look, I got these sharply peaked structures. That's going to cost me a lot of Fourier modes. It's going to pick up my dimensionality of the system. Okay? So, and again, this is a Fourier way of thinking. But here's what motivated it. John sent us his data because we wanted to do one thing with it. We wanted to project this data down on some principal components. Just say, okay, fundamentally, is there really that much difference between this sinusoidal wave and these sharply peaked structures? So what we're going to do is just take simulation data we got from John, line them up in a big matrix. Time 0, time t1, t2, t3. In other words, take slices over one period in time, do an SVD, and what you get out is your singular values here, your modes, and the projection of each one onto these modes. And we can just ask the following question. Well, is this stuff low dimensional? And in fact, if we take the periodic movie I showed you, here's the behavior of this stuff. Here are the singular values, essentially you get out of the SVD. And here's the modal energy. So you have about 82% of the energy in the first mode, then a little bit, maybe 10% in the next mode, a little bit more in the third mode, and then hardly anything. It's telling you that it's primarily 3 degrees of freedom, 3 modes, and there they are. And when you look at the sharply peaked stuff, here are the modes. And it's telling you the same thing. It's primarily 3 degrees of freedom. And if you're using Fourier modes, it's going to be a lot more degrees, right? You're going to have to take a lot of Fourier modes to resolve this. But if you work in this basis, it naturally has the sharply peaked structures already included. Yeah. Yes. So yeah, here are going to be the modes for the one area. Here's going to be the modes for the other area. If we just do the simple, straightforward SVD. Absolutely. So what you try to do is get enough sample points in time that you get a good resolution of the thing over one period.
Not even enough, but if you had clustered things towards the peak of the Stokes wave somewhere else.
Right, and in fact, let's go further with that. One way to calculate these is if you actually use Chebyshev points in time, you can get down to numerical precision on calculating these POD modes. So there's some more details there in how you sample that make a difference here. But for me,
yeah.
Yeah.
Because you could have chosen where you were going to have the clustering in Chebyshev.
That's right.
To be somewhere else.
That's right. Yeah, in fact, you don't have to have a uniform grid at all. Yes, so to your point, don't have to uniform grid. You just have to sample the right spots. In fact, we're going to talk about that sampling idea from a different point of view. But this just tells you something important, which is fundamentally, I don't need to use 1,000 modes here. I just have to use a better basis. This is the optimal projection in L2 sense. Okay, so what we're going to do then is to try to figure out, why don't we just construct all the dynamics then in terms of these modes? I sample, just like you would do in data analysis. What's that?
The modes are time dependent.
Mm-hmm. So remember, there's an amplitude factor that's time dependent, and that will pick up all the time dependency. You're just going to do a separation of time-space. Your spatial modes are here, and then how each one of these modes depends, you have a coefficient that's time dependent. Right? So it's just going to be a simple thing like this. It's just, again, it's the oldest trick in the book. Okay, and then what you want to do is say, if I get this right, it's going to tell me how these evolve in time relative to each other to pick up these behaviors.
The mode appears to depend on whether you know something about the solution you're going to get. Suppose you didn't know it, you know nothing about the solution in advance. For example, the situation do not have peaks at all. Now, how do you choose your mode?
So the way I choose my modes is just directly from the data. I choose my modes from John's computation. Or I can choose them from experiment. Yeah. Let me get to that, because I'm going to show you an example of this as we go. In fact, I'm going to give you sort of after the waterway problem, I'll give you a couple other examples just so we can get a broader perspective on using this technique. So let's go to the infinite depth case. And
One more thing.
yeah.
How does that decay? I mean, you show the 80, 20, and so on. How does it decay at the logarithmic scale?
These are pretty. It's a very slow decay out there. So if you look at it down on a log scale, you see there's very slow decay. But what you do see is the dominance of a few modes, and that's what we're going to do all our dynamics on. Okay, so we're going to just do this projection. Just basically say, here's the amplitude. Here's this dipole piece, just projected onto these modes that we calculate. Okay? And then here is the projection. Who cares? It's just some ODEs now. And here's the point. You'd like to keep this number small. You want to keep a minimal set of modes that will give you everything you need. So instead of using 1,000 modes, 2,000, 10,000 modes, whatever it happens to be, if I can get away with 3, 6, I've done something, right? Okay. Now, each sample of the data can be represented as some projection onto the modes themselves. So here's the full n of the samples. I'm going to chop it off down to little n. So I'm only take a subset. And what I'm going to do is look at the error between the full thing versus my low-dimensional projection. I'll call that the error. And I want to just choose my behavior so that I'm below some tolerance. Okay? Yeah. Oh yeah, good. I'm going to show you the decay in a minute. But it still is. It's not like it just goes to 0 and flattens out, right? It's not like it goes down to numerical. Yeah. In fact, I'll show you the plot here in just a second. Here, this gets to the specific answer. So you see, what we can do is say, what most people do would say, let's just do a Galerkin. That's very well understood, expanded Fourier modes. And why would I do these special POD modes? And here's a partial answer. Let's first of all take a look at this first low amplitude wave, which actually looks pretty sinusoidal. And in fact, you see here the POD modes versus the Fourier, and you don't gain that much by doing POD modes. And here's the die-off as a number of modes. So this answers your question directly. But when you go to structures like this, where you are far from being sinusoidal, here's your decay of the Fourier, which is very slow relative to the decay of your POD modes. So, even within about 10 modes, you have something like 6 orders of magnitude difference in the error. Okay? And by the way, I'm still going to claim, by the way, that these, in some of the problems I'll show you later, Fourier doesn't work at all. Here, Fourier can still work because, maybe you don't have the best Fourier expansion, but you still do a lot better with POD, but I still could do it with Fourier.
How do you get the PODs before the modes?
We'll come to this. So this is, you could say this is a weakness of the problem, which is you say, I still need to do the full computation, or I still need data from somewhere to actually get the modes. But I'm going to address that issue as we go along. Okay. So now here's what we're going to do to try to do. So the way people have often looked at this also in terms of a PDE is to say, let me go to one point, look at the dynamics there, and I don't really care about one point. What I want to do is follow branches of solutions around in some low-dimensional way. So for instance, here is a branch of solutions. These are numerical runs from John's code. And notice as you go up this solution branch, here's the behavior over here. This is sort of looking at the period of the wave. And as you go up this branch, you start going from something that looks fairly sinusoidal all the way up to something that looks like the very sharply peaked. Now, what I want to do is do a full reconstruction of the dynamics as a function of the bifurcation parameter. And so what I need to do is I need to sample from different points of my dynamics. So what I'm going to do is take some sampling of down here and up on this branch here. In fact, the red points tell me where I'm going to pull out some samples. And what I'm going to do with these samples, I'm just going to take this sample here. That's a matrix. Take the next sample, next sample, next sample. I'm just going to put them in a giant matrix, MATLAB, SVD. Drop it down, and I get out the principal components. Okay? And here they are. Here are the first 12 modes. Okay? So here is eta, here is mu, and you can see that essentially, what these need to encapsulate is sort of information all across here. You're looking, in some sense, for the projection of the variance, not just at a single point, but across a whole range of points. And so here are your dominant mode, and down to the 12th mode, same thing here with mu. And what I want to do now is construct all my dynamics in terms of these modes, which you probably, you wouldn't guess, right? I mean, there's some very interesting structure that goes on in these modes. Look, it carries information about the sharply peaked structure that you need if you want to construct this dynamics. These are not simple Fourier modes. And then and part of the way we do this is what's called sequential POD. So if we're going to walk up this branch, and here's a reference for that. So what you do is you sample at one spot. Suppose at the bottom of this branch here. Now, when I come up here, I want to resample, but I've already got some modes out that I want with some tolerance. So I pick out, let's say, the top 2 or 3 modes that matter. When I get up there, with the data I have, I want to project out some new modes where I've projected out the modes I already have. Okay? So I'm going to grab what's extra in this next set. And I keep getting more and more information as I walk up this branch. So that's the sequential POD method. And here you can see the convergence of this method, both in the eta and mu set. And by the way, this is Fourier versus the POD. Now, Fourier does really well here, right? Because on that left end, you're looking like Fourier modes. And when you go up, as you start sampling upwards, walking up the branch, this is where Fourier completely breaks down, and you do really well with these extra modes you have that capture the sharply peaked structure. So when you do this, you can reconstruct a bifurcation diagram, and here's the full reconstruction. And the Fourier only can actually come up to about here, and it can't satisfy your error criteria anymore. And the POD can walk up the whole branch without any problems at all. Okay? Okay. So that's the infinite depth case. And we wrote everything there in terms of eta and mu. And now for finite depth, what we're going to just do is say, well, okay, let's... how do you sample Fourier modes on a boundary that's actually evolving in time? Because we want to actually sample now this dynamics and get the POD modes out in this region here. And so what we do is just make a transformation. This is a very easy solve in the middle. Laplace equals 0 there. Now we just transform this over to a simple boundary up here, but a more difficult problem in the inside, and then we expand. Okay? So a simple transformation. And we do the same thing as before. So, hold on. Let me get back to the slide I was at. Is it? Here we go. Finite depth. Okay. So, in the infinite depth case, we never really took care of the boundary on the bottom, right? It goes to infinity. If we write everything and represent everything in terms of the mu, then we don't actually have to take care of the boundary down there. Okay? In a finite depth case now, you have to solve on the finite domain. You actually have a boundary condition. It's not just going to infinity. It's a finite depth. You have to impose the boundary down there. Okay? So now you're solving in a rectangular box versus semi... Yeah. But
everything is still just living on the two boundaries, right? You just have to solve for sources.
That's right.
So it doesn't seem fundamentally different.
It's not that different. Fundamentally, it's not. I just wanted to illustrate that you can do infinite finite depth. All you're doing is a reconstruction in a little bit different way. Before we were doing POD modes on the mu field. Now we're doing POD directly on the potential inside.
Oh, the bulk.
That's bulk. That's right. And if you do this, here's the bifurcation diagram. Again, we can sample around this curve. Here are our modes. They actually look quite a bit more sinusoidal. And here are the POD modes of the interior of the fluid. Here are the first 16 modes. And we're going to expand in these modes. Okay? And here's the final picture for this, reconstruction of a bifurcation diagram, which is the black line is the full 10 to the minus 24, 25. John likes getting way down there. I'm pretty good with 10 to the minus 2 or 3 because that's my naked eye measure. Looks good to me. So, but that's the full solution. If you do a 6-mode truncation of that system, you get the red line, which is qualitatively correct. If you do the 10-mode, you're pretty much dead on the line. Okay? So how do you think about this? I mean, what we just did is said, let's take this water wave problem. As you saw from John's talk, pretty difficult to solve for this. And granted, there is this idea that we already have to solve for that anyway to sample. But once we have these sampling points, we can reconstruct the full bifurcation diagram as sort of a, if you want, to get it quantitatively correct, a 10 by 10 system. So what does this allow you to do? Well, first of all, you can think about this. Think about where John wants to go next, which is a 3D problem. How long does it take to solve the 3D solve? Days, weeks. We can do this on portable computing platforms because it's low dimensional. We could even do the 3D problem. And if you want to think about it for this problem, you can think about this as a fantastic tool as sort of a multi-resolution time stepper. If you can sample at one point, then you can walk off that point for a while, do a fine scale calculation, and keep following curves around. So we're using the low resolution, high resolution, because the low resolution here, it's only 10 modes. It's trivial, right? You just walk this up. You can do it in MATLAB on your machine. Yeah.
So that means you use the low res till it starts not working very well, and then you do high res again to recomplete the model.
Right. That's right. So you'd in some sense, walk up the branch. You'd maybe get a solution here. You'd walk it up a bit, resample. So it's just like any of these equation-free methods, right? You walk a while, you project, and lift and project to get to the fine scale and macro scale, whatever you need to do. And this will greatly speed up your computation of the branches. Now, one criticism you may have is like, well, okay, you could have done all of this, right, with Galerkin expansion and Fourier modes. So you're working really hard. You have to sample your POD modes. And yes, okay, you did it in 10 modes. Maybe it cost me 40 Fourier modes to get the same thing. Now, I would argue, for one, that if you look at the even more exotic solution John has, that separation of low dimensional to high dimensional is going to get bigger with Fourier versus these PODs. Okay, that's one thing. Second, you can use as a time stepper. So I want to show you an example where if you just use Galerkin with Fourier, nothing works. And so the POD really gets what you want. And here, this comes to a laser problem. And if you want to think about this, just think about it this way. There's a PDE with some dynamics that changes as a function of bifurcation parameter. And here's what we're going to try to model here. It's a laser pulsing instability where in a laser cavity, if you turn on the gain, you get a pulse out. If you turn up the gain, what they really want to do is get bigger and bigger pulses of energy. But instead, it splits. It goes from 1 pulse to 2. You keep adding energy and it splits 2 to 3, 3 to 4. So there's a limit on the pulse energy. And here is the experiment showing this. It goes from 1 to 2 to 3 to 4 to 5 pulses. So your energy in the cavity increases, but now it's split up into a bunch of pulses. And right at the bifurcation point where it splits, some interesting stuff happens. You go from a 1 pulse, it goes through a Hoff bifurcation. So it starts breathing like this, and then it breathes harder, it goes chaotic, and then finally goes to 2 pulses. So that's the transition, and here's a little model for it. And again, like I said, who cares? There's a PDE. There's some dynamics as a function of a bifurcation parameter. I go from 1 pulse to breathing, chaotic, 2 pulses. Okay? And what I'd like to do is capture that dynamics. Now, what we learned from the first part is to say what I need to do is sample. I'm walking through parameter space. And what I want to do is sample from regions where I have some nice stable behavior. So what I'm going to do is I'm going to sample here, here, and here. And all I'm going to do is take this matrix, stack it on top of this matrix, stack it on top of this matrix. Let's leave the chaotic region alone for a minute. So I have these 3 matrices we stack together. I S3D it. In other words, I'm looking for the modes that sort of in some sense are encapsulated in this whole transition. And here are the 6 modes. By the way, I picked 6. We had a cutoff. We wanted to get about 99% of the energy. Okay? And so we picked 6 modes. Now, one of the questions is, can you get all the right structure out with 6 modes? And I want to just show you the end result here, which is focus on this middle picture. This is the bifurcation diagram of the full PDE and of the ODE. Okay? And over here is a blow-up of this left region, here and here. Over here is a blow-up of the right region. So quantitatively, they're off. I'm not going to argue they're the same, and I'm going to tell you why I think they're not the same. But qualitatively, all the bifurcation structure here is exactly the same as you get in the full PDE. First thing you do is you go through a Hopf bifurcation, then you get a period doubling to a torus chaotic, then it jumps to 2. You get all the right features of the bifurcation with 6 modes. Okay? 7, 8, 9, they produce the same stuff. Anything less than 6 will not reproduce this. So in some sense, my claim would be that if you do this with these modes, what you're ultimately doing is doing a global normal form. Normally what we do in bifurcation theory, right, is you zoom in on a local spot, you do your expansion there, and you say, oh, this bifurcation is a Hopf. It's a saddle, whatever it happens to be, right? Because you expand, you throw away all the small terms. This is equivalent to this. With these 6 modes, this is the minimal set that gives me the full global bifurcation behavior. Okay? So I need all 6. Now, why is it only qualitatively correct? Okay, that's one question you could ask. Because, in fact, we have a way to get the modes down to numerical accuracy, and we still can't improve on that. Where did I sample from? The only thing I ever sample from are stable behaviors. Okay? So I look at stable behaviors, and when I go hit this Hopf bifurcation, right, in the full PDE, there lives an unstable mode, an unstable manifold on which the thing will want to go off on. I didn't sample that. So how does my system know about it? It doesn't. Remarkably, it still gets you all the right behavior. It's just that quantitatively, it's not going to go unstable at the same spot because I do not have information about the unstable mode in my calculations. So this is sort of, if you want to think about it, a shortcoming to the method, and something we're kind of working on is how can we make up an unstable direction to give us a signature that what I really want to do is sense when it's going unstable, maybe do a refined sampling there to pick up the unstable mode. And if I did that, then I could perhaps get the bifurcation to happen at exactly the same point, instead of being off by 30%. I get all the right physics, all the right dynamics, that's the thing. Second thing I want to point out in this picture. So there's that issue about it's a global normal form. If you remember, there was the translating chaotic part. Well, there are ways to handle this. So there's some work by Rowley and Marsden, which showed if you have symmetries in your problem, continuous symmetries, you can handle them all, pre-process, take care of these continuous symmetries, and still use the POD. This happens if you have things like translation, rotation. They'll kill you if you just throw something that's translating into a big matrix in SVD. It'll tell you there's tons of modes in there. It's one mode that's moving. So you have to pre-process that. So this is one example, again, where if you try to do Galerkin here, it's garbage. Produces nothing like this. If you try to do Galerkin, you're going to have to use hundreds of Fourier modes. So you just might as well solve it numerically. Here, do this, 6 modes, because you have localized structure. Let me give you another example. And this addresses another issue, which is, okay, so everything I've done so far, you have to do these big simulations to actually get information out of. Well, here's a system in which we're basically saying, actually, why don't we just construct these modes directly from the experimental data? So this is work with this guy, Jeff Riffle. He's now at the University of Washington Biology Department, and he studies this moth here, Sexta manduca, one of the favorite animals to study in these biology labs because they can just chop their head off. The head stays alive for 2 days. And they split it in the middle, put a probe in there, and they can do experiments for 2 days while the thing's just a head. And then when you're done, you throw it in the trash. There are no animal rights advocates for moths currently. Okay, so this is a fantastic toy animal, and here's the experiment. Right at the base of the antenna goes into an olfactory bulb. So there are like 10 to the 6 connections of neurons coming into this bulb, which has something like 10 to the 2. But they're organized in the following way. there are these what are called glomeruli, these little balls. They have like 50 neurons each. They're all connected to each other. And then there's a giant inhibitory neuron that talks to all of them. And then each one of these glomeruli has a connection to the mushroom body or the brain. And they also have a feedback. So the way this works is it applies an odor, and this is really kind of remarkable. So we model this by saying, okay, we have some these interneuron connections. We have these output cells, which are here, some input, and we have direction to send information to the brain. And the way this thing works is remarkable. Jeff takes the data and says, okay, I'm going to apply an odor and see what happens in this olfactory bulb. Odor A, odor B, odor C. And what he observes is the following. Everything is encoded in spatial patterns on this olfactory bulb. So if I apply odor A, all the glomeruli turn off except for maybe these three. These three are going nuts. I apply odor B, all of them are off except maybe these three. So everything's encoded in spatial information. So how would you go about handling this problem? So how does he know this? Well, he actually then does a principal component analysis of just static data. Takes static data and shows that all these odors project down to principal components. So how would you go solve this problem? The data says there's low dimensionality already. It's dumb at this point then to build a model of thousands of neurons. Hopefully I didn't offend anybody with that statement. But in my view, it's all about dimensionality reduction. And what you really want to do is say, recast the whole dynamics in terms of the principal components you already know are there. Right? So you have these principal components directly from experiment. And each one of these principal components is weighted. So each odor has a certain weight to it. So for instance, if I apply stimulus A, it has a certain response. Stimulus B, a certain response. When I apply both together, they compete. At the olfactory bulb, only one odor is sent to the brain. Okay? Odor A or odor B. And they compete on this olfactory bulb. So you have to write a competition model between mode 1, mode 2, mode 3, weighted this way. And by the way, not surprisingly, the strongest weight, female moth. Just a little bit of female moth in a zoo of all kinds of great other smells, and it just goes to the female moth. Hard-coded as a spatial and temporal pattern in there. Explains a lot. All right. And here's the weighting, and we can write down the competition models. I'm not going to go into any details here because it would take too much time, but I did want to illustrate one example of dynamic POD, if you want to think, or a PCA, where you're using no computations, but just take this stuff directly from experiment. Plug it down here. The experiment's telling you the whole system's low dimensional. Don't make it harder than the system's telling you. Use that information, construct all your dynamics in what are the natural modes that you would have never figured out yourself, but the experiment's giving it to you for free in a way. Finally, final one, which is one thing I'm working on with gesture recognition. And computer science is working quite heavily on face gesture recognition issues. In fact, yesterday on CNN's homepage, they're talking about Facebook. And Facebook now, for all Facebook users, they want to scan in everybody's picture. So every face picture that has a face in it, they want to identify it and automatically go through and assign a name to that picture. So it's face recognition technology. If you've ever anybody used Picasso? It's part of Google. Picasso is where you can upload your photos for friends to see. You can go highlight a face and say, please find me in all my pictures that person. And it will do it for you. It goes through, and it's basically using low-dimensional projections of that person's image, doing a correlation score with all the other images, and it'll find all of them. And it trains. It'll give you, these ones we're in doubt about. And you can say yes or no to them, so it's supervised learning. It's all machine learning, all this. In fact, the person who wrote the algorithm for Google is the wife of Ellie Schlieserman, my postdoc, who's working on this with me. Okay? So she's presenting this at SIGGRAPH this year, but that's what Google is using. And Facebook, I think, is using it now, too. Well, we're going to do something different, gestures. I want to stand back. I want to replace using a mouse by just, grab the mouse, 1 click, 2 click, scroll up, scroll down. Okay, that's the start. So you want this thing to recognize that real time. In a gesture set, you have to pre-process your hands. Someone might do it like this. Some might be left-handed. Some might do this. You have to take care of all that. And the pre-processing step is really important. And then what you do is you look for the commonality. In other words, the principal components associated with everybody's hands. Now, how did I get my data sets? I have a coffee machine in my office. And so grad students are walking in the hall. I say, hey, why don't you come have coffee with me? They say, sure, okay. So before I make them an espresso, I say, okay, but I've got to take like 50 pictures on my iPhone. And they have to do all these gestures. And then I make them a coffee. And then I get my next victim. And so I build this huge training set for hands. And it turns out you can sort of get this idea of dimensionality reduction by using the number of modes, for instance, for the one click. Here they are. If you use one mode, 3 modes, 10, 40. Notice with 3 modes with the one finger, you don't get much information. By 10, you do. Now, why is that? Turns out for each hand, if you hold a finger up, everybody's angle is a little different, which means you can't correlate it very well. Notice if you hold up 2 fingers, by 3 modes, I can kind of identify it. Because even if you're doing this, different angles, this little structure here is highly correlated among all hands. So in other words, if you're going to decide on a low-dimensional projection for gestures, you use this, or this one here, which is this. Because here? There can be, exactly. It's all interpretation. And by the way, even here, look at the difference here between an open hand, because when you do an opening, everybody's opening will be slightly different. Everybody's angle will be slightly different. So, by 3, you can't see anything. By 10, you can. But notice by 3, because when you do this, even if you have a different orientation, it doesn't matter. So, for instance, I could ask the question the different way, which is, you get 2 gestures. What 2 gestures are the best to use out of the 5? Clearly these 2. They're the lowest dimensional projections. Now, we start off with a gesture, but here's the big goal of this. And again, it's going to relate back to the dynamic POD, which is, I have an iPhone. I know some of you are BlackBerry fans, and eventually these BlackBerry guys will get on iPhones. Just a matter of time. But there's this free app on the iPhone called Dragon, right? And this is just a dictation. You just push a button and you speak. You can go off on a whole paragraph, stop, and then you can send it as a text or an email. It's pretty remarkable, especially one of the things I'm not good at. The 20-year-olds in my class can type Moby Dick in like 5 minutes with their thumbs. And it takes me like half an hour to say hello, right? So what I love is this dictation. If I've sent something longer than a paragraph, I just dictate it, sends it. And it's very accurate. So imagine doing something similar like this, but with gestures. You run into somebody who does not speak English, speaks sign language. You could take that same iPhone, and they're trying to communicate something to you. You could just start filming. They would do their gestures. So now this is where the dynamic part comes in, because the gestures themselves have movement, and you have to film blocks of time and now project trajectories in this low-dimensional space. So there's no F equals MA in this. However, there are now dynamical trajectories if you want to think about it as with a certain number of fixed points, which are the gestures. And anytime you get close enough to one of these fixed points, it says, I got a hit over here. You just did world or born, something like this. And so the idea would be you're still using this idea of projection of PCA, and again, all data-driven. And hopefully that gives you an idea of what...
This guy's asking, why do you have only 2 arms?
Okay. Good question, of course. So I'm going to conclude just with this simple thing. When I started teaching that data analysis course, I found this review article by Gil Strang. And he wrote here the SVD, high point of linear algebra. And when I first started this class, I didn't really believe that statement. I thought, okay, this is just one person's opinion who's, saying what they like best. But it turns out, in doing all this, I've really found this is just, and many of you know how powerful the technique is, but a lot of the technique has been applied towards this computer science statistics community. But in these examples I've showed, we've had great success just bringing the dynamics into it. Take your PDE, project stuff down. When does it not work? The one case where it's pathological in terms of not working is if your matrix A is non-normal. So Clancy Rowley has this example where to get the dynamics right, he takes mode 1, 2, 3, and 17. If you don't take mode 17 has 17th most amount of energy. But mode 17 is key to driving the interchange dynamics. His cases were all non-normal matrices. As far as I can tell, if you have a normal matrix, you just take the top modes. And there's other projections. I think Esteban also works on these cases where maybe you don't want to project onto the L2. That's what SVD does. Maybe there's a different projection to use. But either way, this is a nice recasting, I think, of the dynamics. So that's all I got to say.